Okay guys, let's take a look at today's lesson. So today's lesson is about limits of sequences. Basically what our job is going to be today is to determine if a sequence converges or diverges. So let's talk about that. We have talked about that concept before. Let's just go over it. So a sequence is going to converge or is convergent if it approaches a specific value. In other words, if the terms of the sequence, as you list them, so remember a sequence is a list of terms, whereas a series is all those terms being added up. So if the actual values of each term is approaching a specific number, we would say that the sequence converges. Okay? If the values of each individual term are not approaching a specific number, maybe they're going to infinity, or maybe they're doing something crazy, like they're flipping back and forth between -5 and 5 or something, then we would say that the sequence diverges or is divergent. So let's do a reminder of these special limits right here that we looked at several months ago. Okay, so if you recall, if we have a fraction and the denominator it grows without bound, it gets bigger and bigger and bigger, that means this entire fraction is going to get smaller and smaller and smaller and basically tend to 0. Whether we are headed to positive or negative infinity, that would be the case. We either tend to 0 from above or we tend to 0 from below. So we're basically going to go to 0. And that's a concept that we're going to need today when we look at determining whether a sequence converges or diverges. Because what we're going to do is we're going to take the limit to infinity as n goes to infinity. That's how we determine whether a sequence converges or diverges. Alright, so let's look at that. Let's do some examples. The first example is there just as a reminder, just to remind you how we do limits to infinity. If you recall, the technique that we used previously is we would look to see which has the highest exponent. It doesn't matter whether it's in the numerator or denominator. Wherever the highest one is, we multiply by 1 over the largest over 1 over the largest. Of course, we can only multiply by the number 1, so they have to be the same. Alright, so I'm going to distribute this to each of the terms in the numerator and the denominator. I'm going to do it basically all at once and simplify as I go. Hopefully that's not too troubling. So when I multiply 3x squared times 1 over x squared, I get 3. When I multiply negative x times 1 over x squared, I get negative 1 over x. When I multiply negative 2 times 1 over x squared, I get negative 2 over x squared. Okay, and then for the denominator, when I multiply 1 over x squared times 5x squared, I get 5. And now I'm going to multiply 1 over x squared times 4x. That gives me 4 over x. And lastly, 1 over x squared times 1 is 1 over x squared. Now what I like to do is that the reason that we use this technique is so that we can get little pieces of this limit to be in that special form, the special limit that we looked at on the last slide. And notice how this is in that special form. As the denominator grows larger and larger, this fraction is going to tend to 0. And that's going to happen when I have a constant in the numerator and the denominator grows without bound. So that's going to go to 0 and 0 and 0. I like to circle them so that I kind of, in my mind, that tells me, okay, those are 0, and I can know that they're 0. So basically what I'm left with is what this limit is tending to, which is 3/5. Okay, so that's just a reminder on how to do limits to infinity. Now when we are asked to tell if the following sequences converge or diverge, and we're just looking at them, the test we're supposed to do is we're supposed to take the limit to infinity as n goes to infinity. Now it's not going to typically be set up for you like that, it's just you have to know that that's what you're supposed to do. So that's what we'll do. We're going to investigate this by taking the limit as n goes to infinity of 7n cubed over 4n squared minus 5. Now here, if we look in the numerator and denominator, we see that the largest power is 3. So I'm going to multiply by 1 over x cubed over 1 over x cubed. So then we get the limit as n goes to infinity. So we're just going to distribute and simplify all at the same time. So in the numerator we get 7. in the denominator we get 4 over x minus 5 over x cubed. Okay, so we look at that and we look for the little special limits and we see there's a couple of them. Here's the special limit, that's going to tend to 0, that's going to tend to 0. So this is basically going to 7 over 0. Okay, so we know we can't divide by 0, that's bad, right? So that is undefined. And what does that mean? Well, that means that there's apparently an asymptote there at, or basically it doesn't approach anything. It doesn't approach anything. It just continues on forever, either going to positive infinity or negative infinity, or bouncing back and forth, just depending. In this particular case, if we look at this and think, if I put larger and larger n values in here, 1, 100, 1,000, a million, what's going to happen? Am I going to get bigger numbers or smaller numbers? Well, I'm going to get larger numbers, right? So we would say that this is divergent. And if they ask to see where it's going, it's divergent basically to infinity. It's going to infinity. Okay. All right, so for our last problem, this is a bit complex. So what I would like to do is just kind of break it apart into little pieces. We know from past experience that this is just all multiplying, right? It doesn't matter what order we multiply in. 2 times 3 is the same thing as 3 times 2. And we've been working with that since, elementary school. It's fine. So I'm going to just break this up a little bit so it makes it a little easier for me to understand what's going on. So I'm going to do the limit as n goes to infinity. And what I would like to do is just deal with the numbers. So let's do 15, 6, just bring those together, times. I'm going to take this n and put it with one of those, so n over n times. I'm going to take this n plus 1 and put it with one of these. And then I'm going to take this 2n plus 1 and put it with one of those. And so let's recap and make sure we haven't done anything incorrect. So if I multiply the bottom 6 times n times n times n, I do get 6n cubed. And if I multiply the top 5 times n plus 1 times 2n plus 1, I do get the numerator or the top. So we're fine. It's okay to rewrite it like that. One of the benefits of doing this is we can work on simplifying it because it's just kind of a big mess. How do we even know what to do? Here I know that n over n is 1, so I would simplify that to be 1. Also, I would going to pull this fraction out to the front. That's an allowable limit. You can pull numbers out to the front. And I'm going to rewrite these. So I could multiply by 1 over n over 1 over n, but I'm going to try to make it look a little bit more simple rather than making it more complex. So let's rewrite it. So I have 15, 6. That was a 1. I'm going to rewrite this fraction as we're multiplying. So n over n is 1 plus 1 over n. So it just seems easier to me to do that because this is the special limit. I don't have to do any of this to get to the special limit. I already have it. Times, we'll do the same thing over here. So I have 2n over n, which is 2 plus 1 over n. Okay, and I did a little bit of simplifying as I went. Hopefully that's okay. Alright, so I have 15, 6, limit n goes to infinity of 1 plus 1 over n times 2 plus 1 over n. Okay, that's just an extra little step. Do you have to do that step? No, it was kind of fun. So let's take the limit now. This piece tends to 0 and this tends to 0. So what do we have left? We have 15, 6 times 1 plus 0 is 1 times 2 plus 0 is 2. So we basically have 15, 6 times 2, which would be what, 15 thirds or 5. So what that tells us is that this sequence is going to converge to 5. Okay. And that is the lesson for today.